Hello all and welcome to my presentation. Today I'll be talking about my project SiegeBreaker, which is about building a practical decoy routing solution with the help of software defined networks. I am Piyush Kumar Sharma and this work has been done in collaboration with some wonderful colleagues which are Devashish, Himanshu, Chaitanya, Anish, Vinayak, HB and Sambuddho. Censorship, as we all know, is on the rise. There are various countries which try to restrict access to some form of content to the users, and this restriction or filtering is achieved with the help of various mechanisms, which are IP filtering, DNS blocking, deep packet inspection, and so on. As a solution, there are various circumvention systems which have been proposed by the researchers, and the most popular ones of these solutions which the users generally use are proxies, VPNs and Tor. However, most of these proxy based solutions suffer from a weakness, that is they are relatively easy to block once their IP has been discovered. Decoy routing is a new approach and it tries to make it very difficult for the adversary to block such a system. That is, even if the adversary knows that such a system is present, it will not be easy for the adversary to completely block it. There are various decoy routing systems which have been proposed, and before going into detail, I would like to describe you in brief about how a decoy routing system generally works. As you know, there is a client which resides in the census regime which want to access a blog website which we term as covert destination or CD. However, there are a few websites which the clients is allowed to access, which is the allowed.com in our case, or the overt destination or OD. A client would initiate a normal request to the overt destination so that there is no suspicion to the adversary. However, on the path from the client to the overt destination, there will be a smart router sitting in between which will recognize with the help of a secret handshake that these packets which are being sent from the client to OD are actually intended for the covert destination, and it will on real time deflect these packets to the covert destination and the client will be able to access CD content. However, there are various challenges for in the existing decoy routing approaches. These challenges involve some advanced form of attacks such as traffic analysis, or some specific attacks such as routing around decoys where the adversaries try to bypass these smart routers altogether. Secondly, there are challenges with relation to deployment. How will we place these routers, where will we place these routers, and so on. The problems which we are more interested in are the performance bottlenecks. That is, if the systems are not able to provide good performance, then the users will anyways not be able to use it. Secondly, the existing decoy routing design tries to analyze all the flows that is traversing through an ISP, and these flows are analyzed by the DR operators, and this might lead to some sort of privacy breaches for the non-decoy routing community, because non-decoy routing flows should ideally not be analyzed by the decoy routing maintainers. So a word of motivation for SiegeBreaker, as you can see from the diagram that and from the description of decoy routing, that there is a smart router which should ideally be able to do all such operations. However, the routers which we have currently are not capable of performing such operations, and due to that they offload this functionality to a commodity server. This commodity server now, which in the diagram is marked as DR proxy, now analyzes all the traffic that is traversing through an ISP, and this leads to a performance bottleneck. Moreover, all the traffic that is traversing through this router will now be inspected by this DR proxy. This, as I mentioned earlier, can be a privacy invasion for non-decoy routing flows, because the ISP is allowed to access the content which the client is accessing. However, the third-party maintainers such as decoy routing maintainers should not be allowed to do so. Thus, if we talk about the overall design, that is to reduce the overall load on the system and to analyze only the decoy routing flows, we make a key observation, that is, we need to basically identify only the DR flows without inspecting non-DR ones. This can serve us both the purpose, that is to improve on the performance as well as to preserve the privacy of non-DR users. And this we think can be achieved with the help of software defined preconfigurable switches or SDNs. I'll give you a brief background of SDNs. So software defined networks are a new networking paradigm wherein the functionality of a single networking device is split into two entities, which is the control plane and the data plane. The control plane, which is managed by the SDN controller, is basically the brain of the ISP or brain of the network, and it performs most of the complex network operations such as deciding routing policies or some access controls and so on. The SDN switch, on the other hand, is only given the task of forwarding the flows at line rates, and this it does by matching the flows based on the flow tables. These flow tables are analogous to routing tables. Moreover, the controller exercises its control over the network by updating these flow tables in the SDN switches. Having said that, we can move ahead with the design of SiegeBreaker, and as you can see in the diagram, there is a slight modification that the friendly ISP which deploys the Decoy routers, there is a SDN switch, but along with that there is a controller which can update its flow table entries. There is a secret proxy which is analogous to DR proxy. The main points which you'd like to highlight or the assumptions is that the controller and SDN switches belong to the SDN ISP, whereas the DR proxy or the secret proxy in our case will be managed by third-party maintainers, and it can be analogous to Tor relays, as we know. That is, the secret proxy can be within the ISP, can be anywhere on the internet. Thirdly, we assume that the SiegeBreaker client already has access to the email ID of the controller before initiating the decoy routing session. The reason for that will become clear shortly. So the SiegeBreaker has been protocol has been divided basically into three phases. These phases are bootstrapping, hijacking, and proxying. The aim of the bootstrapping phase is to let the controller identify decoy routing flows without inspecting the non-decoy routing flows. So we achieve this with the help of a new mechanism wherein a client initially informs the controller with the help of some out-of-band channel. In our case, we use email as that out-of-band channel, that he'll be coming after a while and he will be demanding decoy routing service. In this email, it contains information which will help the controller identify that it is a legitimate decoy routing client. In our design, we use the initial sequence number as the secret message. So the client initiates by sending an email. It contains the initial sequence number along with some parameters which are required to derive the secret key and so on. As soon as the controller receives this email, it installs a rule in the SDN switch telling it to divert all the client and OD traffic, source, client and destination over destination to itself, so that it can analyze that traffic. The client, as it said, would initiate a normal TCP connection with the actual intended destination, that is the OD, and it will set the sequence number in this packet, in the initial SYN packet, to that it sent in the previous email. This packet would encounter the SDN switch, and by the virtue of the rule that is installed in this switch, this packet will be redirected to the controller. The controller will match this initial sequence number with the one it originally received in the email, and this will confirm to the controller that it is a legitimate decoy routing client. After that, it will let the SYN packet go as is to the OD, and following that, the client performs the remaining TCP handshake and the TLS handshake. With this completes the bootstrapping phase of SiegeBreaker. And we can move on to the next phase, which is the hijacking phase. The hijacking phase deals with transferring the client OD state to the secret proxy, which will be serving the covert destination content to the client. Now, as we know, the last step of the bootstrapping phase was that the TCP and the TLS handshakes were complete. After the TLS handshake is complete, like a normal client, it will send a normal HTTP GET request destined to the OD. Again, this packet will be redirected to the controller, and at this point, the controller will now install a rule in the SDN switch to now redirect all the client OD traffic not to the controller but to a secret proxy, and the secret proxy can obviously serve the client its intended covert destination. Along with that step, the controller also informs the secret proxy about some information which the secret proxy requires to take control of the connection. That is the TLS header that was sent in step 5, along with the over destination IP with which the client is connecting, and so on. The secret proxy, on receiving such a packet, would first close the client OD connection, and so that there is no suspicion from the adversary's end. And after that, it will send a confirmation packet to the client informing him that that the decoy routing session has been initiated, and now you can try to access the covert destination. The client, on receiving this packet, validates this packet, and it confirms that his decoy routing has been confirmed. Additionally, client also derives the session key with which it will be talking to the SP or the secret proxy. This brings us to the end of hijacking phase, and we can move on to the proxying phase. In the proxying phase, the client, since it derived the session key, it sends the encrypted content encrypted with the session key. The secret proxy also derives the session keys, and then it extracts the covert destination URL, takes its content from the CD and returns it back to the client by pretending it to be OD. So this completes all the 3 phases of SiegeBreaker. So this was the walkthrough, and what have we been able to achieve with this design is that we have been able to separate the concerns. That is, we have been able to separate out different operations that are performed in a normal decoy routing system. These operations are splitted between the controller, which identifies the potential DR flows with the help of an out-of-band channel such as email. It instructs the SDN switches to redirect traffic on the fly, and the SDN switch forwards the packets at line speeds, whether it be decoy routing packets or the non-decoy routing packets. And similarly, the SPs handled only the decoy routing flows so that it can concentrate on serving them better. And in order to increase the performance, we also implement flow and congestion control at the SP. Along with that, the SiegeBreaker protocol also ensures that it is resilient to replay protection, as well as it provides perfect forward secrecy. Overall, this helps us achieve privacy preservation of non-DR flows, as you know that the secret proxy, which will be maintained by the DR maintainers, only handles the decoy routing flows, and there is an overall performance gain because the amount of traffic that we have to analyze now has reduced dramatically. That is, we only analyze the decoy routing flows, and we all know that the range of non-decoy routing flows is really huge. Having said that, we also did evaluation of our setup, evaluation of SiegeBreaker, and as you can see, I'll try on the left that we have our general setup, wherein there are various clients which are behind a firewall, and they are not allowed to access any content to the covert destination. After the purview of the firewall is the SDN switch, which is managed by a controller. It has access to OD, CD, proxy, and everything. And proxy and CD are set up somewhere on the internet. So the experiments were performed, were divided into 2 categories. One were the in-lab experiments, and the second were the internet experiments. The in-lab experiments basically dealt with SiegeBreaker's performance in the presence of controlled cross traffic. Also, we tried to test the flow and congestion control, which we have implemented in our protocol. Internet experiments tried to test SiegeBreaker performance in realistic scenarios. For that, we deployed SiegeBreaker in our university network. We varied the load and cross traffic. We also varied the load and cross traffic at the switch. We used a commercial SDN switch, which is HP3500YL for all our experiments. As for the results, you can see that the first result shows the amount of time it took for SiegeBreaker to download a file of various sizes, starting from 100 MB going all the way to 1 GB. As you can see that the download time was comparable to direct downloads such as wget. Secondly, before going into the details of the second result, I have mentioned it multiple times that we implemented flow and congestion control. I'd like to elaborate a bit on that front. As we know that the connection between the client and OD is a real one. However, after the controller recognizes this request, the SP actually terminates the connection between the client and OD, and it tries to establish the connection between client and SP. However, this connection between the client and SP is not an actual. That is, the kernels of both the devices are not of both the client and the SP are not aware that this is a normal connection. So we implemented the flow and congestion control in order to ensure reliability and also that they utilize the maximum bandwidth on the channel. And as you can see from the results that when we ran SiegeBreaker and wget on the same link, they were able to share the link equally, suggesting that it performs well. Moving on to the internet experiments, we downloaded the default web pages of Alexa top 500 websites, and we compared those download times with the one with wget. And the average download time for SiegeBreaker was 1.8 seconds and wget was 1.7 seconds. Similarly, we downloaded file size of various sizes. These files were hosted on cloud servers and we accessed them using both wget and SiegeBreaker. And as you can again see that the time taken was almost comparable. We would also like to mention that SiegeBreaker is also integrated in a browser and it can load static and dynamic web pages easily. We also varied a lot of cross traffic at the switch just to test how much the switch is able to handle. For that, we connected 15 physical machines to the SDN switch, as you can see from the diagram, all the while when the decoy routing client was trying to access the CD, and we tried to analyze how the performance varies in the presence of this cross traffic. As you can see from the results that on the left, when the cross traffic was approximately 15 Gbps, the performance of SiegeBreaker was again comparable to wget, and similarly we used Apache benchmark to generate a lot of flows, and even in the presence of 50,000 flows, the SiegeBreaker was having good performance. Overall, the insights from the results is that the performance of SiegeBreaker was comparable to direct TCP downloads, as we all know, and this performance was achieved with the help of multiple design choices. One of them being separating the different operations of decoy routing, then using a separate signaling mechanism so that we can isolate the decoy routing flows, using actual SDN switches to redirect traffic such that they do that efficiently, and also implementing the flow and congestion control between the client and SP, which not only provides reliability but also helps us to attain good performance. There are some salient features of SiegeBreaker in the fact that we tested SiegeBreaker for a varied workload, which include not only the websites or the web pages, but went on to download 1 GB file content going to 1 GB. Similarly, we used real routers to implement our prototype, and we were able to provide privacy for non-DR clients. We handled asymmetric routing and so on. However, there are some limitations in that we are not able to defend against traffic analysis, and this is an important part of future work. So is the testing of SiegeBreaker in a real ISP and extending it to other decoy routing schemes. Overall, to conclude, in this research, we propose a new decoy routing system, which is SiegeBreaker. We were able to handle the performance bottleneck and the privacy preserving issue with the help of a design which separated the concerns of decoy routing into multiple entities. These include the controller inspecting only the decoy routing flows, the switch forwarding packets at line speeds, and the secret proxy handling the DR flows, thereby preserving the overall privacy. In all our experiments and thorough evaluation, we observed that the SiegeBreaker performs comparably well in comparison to direct TCP downloads such as wget, and that's all from my side. So thank you for listening to the PPT, and I'm open to questions now.